Okay, so I'm going to try to rein myself in. I'm not used to trying to put lecture videos online. I'm glad to see some of you at least are watching them. I'm going to try not to repeat my lecture video in lecture, here live. So maybe that's comments more for me than for you. What I do want to do is encourage you all to ask questions and things that you don't understand coming out of the book or lecture videos. And actually, so I've got a question already, and that it asks about work. So just as preface to this, I'm going to finish up talking about ramps today, try to make sure that you're all well prepared for the problem set, which is due on Wednesday. I do encourage all of you that haven't looked at it yet, look at it. Get on that website so that you don't get stuck at the last minute, because I can't promise I'll be there to rescue you. Okay, so back to the question. The question asks about negative work and how does the distance go into that? And I want to make sure that you're comfortable with work, or as comfortable as you can be. It is the mechanical means for transferring energy from one thing to another. The word mechanical is in there. Why? It's because it will turn out there's another way to transfer energy, and that's the thermal way. Later on, we'll see that you can transfer energy as heat. If you're hotter than something else and you touch it, heat will flow from you to it, and you will lose energy, it will gain energy. That's the other way. It's not entirely separate from work, as we'll see, but so here I am talking about mechanical stuff. Heat and temperature, all that's in our future. Here's the idea. You're all familiar with working with money, so that's my go-to analogy for talking about energy. With money, you can give somebody dollar bills, and as you do that, your store of money goes down, and their store of money goes up. And assuming that you're not printing money or destroying money with burning it up, whatever, it's a conserved quantity. It moves around between people, and watching it move is useful. We obviously pay a lot of attention to the movement of money. So you can give somebody positive dollar bills, the usual thing you're used to, but it turns out you can also give debt. So suppose you racked up credit card bills and mortgage on your, I don't know, whatever, you bought a second or third house, whatever, okay? If you give somebody your debt, you give them your credit card bills, you give them your mortgage, you're giving them negative amounts of money. As you give away your $10, let's hope your small credit card debt, you give them your negative $10, that debt, your worth goes up, theirs goes down. They suddenly have a liability they have to deal with. Okay, so it is possible to pass off negative amounts of money. So, with work, you can transfer your energy to something by doing positive amounts of work. And the rule for that is it's strict and simple. You have to push on it, and it has to move. Not you, it has to move in the direction of your force. To the extent that it moves sideways, perpendicular to your force, that doesn't count. So if I push up on the ball, which I am doing, and it moves up, I've done work on it. And you might think that, well, this is just some lawyer sitting around deciding on the rules and legislating all that stuff. No, it's the way the universe works. We have no control over this mechanism for transferring energy. When you do the physics laws mathematically and look at how they work out, this is how work has to be. And again, it will be the same in any other civilization anywhere in the universe. So you push on it, it moves distance in the direction of your push. Doesn't matter whether it's accelerating, you're accelerating, any of those things, none of that matters. It's a question of force and distance. Questions at that point? You're okay with that? Yeah, Rebecca. Why does it have to move in the direction that you push it? Because if, for example, it doesn't move at all, I'm pushing on it, it's not moving, I'm not changing its situation. Energy is a characteristic of your situation. So that the ball here it's the same now, it's the same now, it's the same now. The fact that it didn't move means its situation hasn't changed. It has nothing new added to it. So it's not surprising that its energy is not changing, therefore I'm not doing work on it. The only way to change its situation in a way that involves energy going into it is for it to move in the direction I push. And you can see now it's able to do things it couldn't do before. So I really have transferred something to it. If instead I move sideways, So I'm pushing up, moving it sideways. And there is a little complication because I got to get started moving, and that involves giving it a little energy. I can come back to that in a second. But neglecting the little push I have to give it to get it started. Now as I move horizontally at constant velocity, I'm pushing up, but it's moving the wrong way. It's moving at right angles to my push. And that doesn't change I'll stop again. It doesn't change its situation either. It's not able to do anything that it couldn't do before. I have to go up in the direction of its push. Same with imagine a rubber band. Imagine I've got a real strong rubber band. If I just pull on it, nothing. But if I stretch it, now I've packed it full of energy. The act that I pulled outward on it with the hand on the left, and it moved to the left, I did work on it. Is that helpful? So if you start looking at you can look at the rules mathematically, and of course it works this way, but that's not enlightening. If you just think in terms of the energy you're putting in either goes into forces, which is what are called potential energies. It goes into the energy stored in the forces, in which case sort of stretching them makes sense to be packing them full of energy, or it goes into motion. And actually, if you look at throwing a ball, the energy of motion is called kinetic energy. So here I'm doing work, packing energy into the ball's gravitational potential energy. It's stored in the force of gravity, and it can come back out. There are lots of potential energies. We'll come back to them. The other style of energy, or complete type of energy, is the energy of motion. And if I throw the ball, I have to, starting from rest, I have to push on it. I'm going to make it throw it to the right. I have to push it to your right to make it accelerate to the right, and it has to begin moving. If I just push on it, well, how can I not get it moving? I have to fight it with another force. That's boring. But the act of throwing inevitably involves pushing it in the direction you're throwing and having it move in the direction you're throwing. Because you have to chase it as it begins to accelerate. You have to keep going and keep pushing. So as you throw a ball, that involved work. Can you visualize the act of throwing involving pushing it and having it move in the direction of your force? So that's positive work. And actually, we can look in negative work, which is the question. If you push it and it moves at right angles to your work, nothing. Right angles to your force, nothing. But if it moves opposite your force, you do a negative amount of work. You're actually, if you get down into the calculation of the work, the force and the distance and the direction of the force, they're both vectors. I mean, it's sad but true. The force is a vector. In this case, it's upward. So it's a certain amount of push upward. And the distance traveled is a certain distance upward. So if you take those two vectors, if the two vectors, the force vector and the distance vector, if they're in the same direction, positive. If they're in opposite directions, negative. If they're cockeyed and stuff, now it's a little complicated. And you just ignore the part of one of the vectors that doesn't point, that points at right angles to the other vector. Yeah. If I do two parts of work, your question is, if I do two parts of work, one positive and one negative, do they cancel out? Is that okay? Yes. Here, I start with the ball like this. It's got a certain amount of energy, right, associated with its being kind of head high. If I lift it up, I'm doing positive work on it. It now has more energy than it had before, and I have less, having given it to there. And it's a perfect transfer. Every last smidgen has moved. Okay, none destroyed, none created. When I lower it, in which case I'm pushing up, but it's going downward, they're in opposite directions. I did negative work on it. I sucked all the energy out that I put in. It's back to where it was. And this is why in part, why work and energy are so useful. And one of the first things that shows up here in this kind of story is lifting something and lowering it back to where it started from involves no overall transfer of energy at all. And so you can't tell whether I went up and back. If we turn the lights out, and I'm like this before, and I'm like this after, you can't even tell whether I went up and down. There's no indication of it, and the ball has the same energy either way. Is that okay? And so where I'm dreaming of being able to get to, but I can't quite justify this in a very short story, is you all know that when you go hiking somewhere. For every uphill you go through a downhill. It's never happened that you've walked uphill. It may feel like it, but it's never happened that you've walked uphill the entire hike and come back to where you started from. I mean, it shows up in an Escher drawing or something like that, but it can never show up in our real universe because that involves you destroying energy or creating energy out of nothing. If you do a round trip and come back to where you are, you have the same energy you started from. So if you invested energy on one way, you got to take it back out the other way. I don't know whether that's followable, and I won't try to dwell on it because I'll get lost for too long. Other questions? So, yeah, David. So David's question is when I throw a ball, am I doing work on it until it leaves my hand? Yes. If I am pushing it forward and it's moving forward, I'm continuing to do work on it. And this is one of the reasons why to throw a ball really fast and hard, you want to push it for as long a distance as you can. You obviously want to push it as hard as you can, but you also want to chase it as long as you can. You can't throw a ball very fast if you only go a little distance. So a baseball pitcher is throwing 100-mile-an-hour fastballs. We'll start way back here with the ball and chase it all the way to there, pushing the whole way, pouring more energy into it. Is that okay? The other thing is when you catch the ball, think about the catching process. Okay, I'll catch it, whoosh, like that. Notice what's happening with the ball. It came in with kinetic energy. The whole trip is complicated. I throw it with kinetic energy. It turns that kinetic energy into gravitational potential up here. It comes back down. It's back into kinetic, and I catch it. And when I catch it, I let it push on me, and I let it move my hands in the direction of the push. I take the energy out of it. So catching a ball, throwing a ball involves putting energy in. Catching a ball involves sucking the energy out, letting it do work on you. So the mechanics of all that make sense. If you try to take the energy out over a very short distance by not letting your hands move much, it will happen by way of a big force for a short distance, like getting hit with a hammer. If you give with it, like catching an egg, you'll take the energy out of it with a gentle force over a long distance. So this is all, the point of this, and why I'm on this stuff is, these are useful observations. They explain some of the things you just do naturally when you're playing a catch with somebody. You don't catch the ball like that on your hand. It bounces off, for example. Other questions? Oh, come on. Do positive and negative energy involved? Are they associated with velocity increasing and decreasing? Yes, in the act of if you're playing with the ball and we're not worried about going up and down, which involves gravitational potential energy. If you're just simply playing catch with somebody back and forth, as you put energy into the ball, it's going to go primarily into the ball's energy of motion. It's kinetic energy. It's going to go faster. And as you take the energy out, it's going to go slower. And so that's what you're doing all the time when you're playing catch. You're putting energy in, taking energy out, back and forth. All right? How does a 90-degree angle not do any work? Why is it that when you push something one way and it moves at right angles to that, you do no work on it? Among other things, it's in the middle between doing positive work and doing negative work. It's right there at that. The fact that the vectors are at right angles to one another, the push and the motion are at right angles. Can I give you a good justification for why that involves no transfer of energy? It's the same as suppose you and a friend are pulling on a bungee cord. So I've got one end of the bungee cord. If I pull away from my friend with my piece, I'm pulling on it that way, and it's moving that way. I did work on it. Energy really is now in the bungee cord and or my friend. Okay. On the other hand, if I gave in, I've done negative work on the bungee cord. I've sucked energy out of it. But if I go sideways, I haven't stretched the cord or unstretched the cord or moved my friend in any way. I've just done nothing. It doesn't contribute. It doesn't change the energy in the system in front of me. I'm waving my hands wildly because it's not exactly like, but if you do the mathematics part, it will come up that you just didn't do anything. You did not transfer or receive any energy. Okay? Okay. So this is the last of my collected questions here is so I lift the ball up and down and up and down. Of course, I get tired. And you know what's happening? When I lift the ball up, I am taking chemical potential energy out of me, energy that I acquired by eating things and breathing. So I'm using up energy that's in those chemicals. It's now in the ball, and it's in the ball in the form of gravitational potential energy. When I lower the ball back down, the energy goes back into me, but it doesn't go back into chemical potential energy. I'm not recreating my food. Where did it go? It gets broken up into little pieces. The energy goes into me and gets broken up into little pieces and sprinkled around me in all little portions statistically. And that type of energy is known as thermal energy. It's the energy it's in everything. We're full of it. We're full of this thermal energy. It's the little random motions of the particles from which we're made. And because they're moving, they have kinetic energy. And because they're pushing against each other on and off, they have potential energies. And the energy is rattling around inside all the little atoms and molecules, which are jiggling wildly. Everything in this room is doing this. You don't notice them, by and large. There are ways in which you can tell that stuff's going on. For example, if I opened a bottle of perfume here, you would pretty soon notice that there's a bottle of perfume open up here, even though nothing obviously moved in the room. And that's because the little atoms and molecules of perfume would have been jiggling around, and they will drift because of this thermal motion and diffuse through the room, and you'll smell them eventually, and there's the whole statistics of that. So this is going on all the time. And we can detect the presence of that thermal energy. It's very important to life in every sorts of ways. We can detect it by temperature. It's associated with temperature. The more of it you got, the higher your temperature will be. And so as I'm going up, chemical potential energy went into the ball. Down, energy came out of the ball, went into me, it's thermal energy. Out of chemical, into me. I'll get hotter and hotter because I'm just chewing up this energy and turning it into thermal energy, which then drifts out of me by the other way in which energy moves as heat, from hot things to cold things. But that's not for now, that's for the future. There's also a question that would come up like, if I just hold this ball here all day, I will get tired. And why isn't the ball receiving energy? And because I'm not doing work on it. I'm sorry, I'm not doing work on it. No force, force yes, distance no. So I'm not doing any work on it, but yet I get tired. What I'm doing is I am burning up food energy trying to imitate a statue. I'm just going to get hot. So we're not good statues by nature. We waste energy just trying to hold a steady position. Just how we're made. All right? Okay, any other questions about work and energy? Things you're wondering about. Obviously, energy is an enormous thing in your daily life, whether you sort of pay attention to it or not. It's a pressing issue for society. Having talked about the existence of thermal energy, there's no shortage of energy itself. Thermal energy is abundant. It's all over the place. It's just not very useful. You can't, once you have taken beautiful energy that's suitable for doing work, like the chemical potential energy that allowed me to lift the ball, you can't, and you turned it into thermal energy. It's still there. Energy is a conserved quantity. You can't get rid of this stuff. It's there, but you can't use it as easily. It will not do work directly. So we'll talk about ways in which you can use thermal energy to do work. It's complicated. You have to allow heat to flow from a hot thing to a cold thing in order to use thermal energy to do work. Alas, there is one of these objects that is moving heat from hot to cold to do interesting stuff, and it's called Hurricane Florence. And it is what's known as a heat engine. We'll come to heat engines, down the road. These are devices that create work, that obtain work, that are able to do work. Why? Because heat is flowing from hot to cold, hot seawater to the cold rest of the world, and that is the source of energy for this, and it can do a lot of work that we won't want. Okay? All right. So ramps. Let me finish ramps. Just as background for this, since I didn't, the only piece I want to drag out of the lecture video and point out to you is that when the ramp is flat like that, as in not a ramp, a sidewalk, the wagon is perfectly supported. The support force from the horizontal sidewalk is directed straight up. It's perpendicular to the horizontal sidewalk, that's straight up. So the sidewalk pushes straight up on the wagon's weight is straight down, they negotiate a bit, and pretty soon the wagon's perfectly supported. No more, not too much, not too little. But if we tilt the sidewalk into a ramp like that, the cancellation fails. And the cancellation fails because the ramp's still exerting a support force on the wagon. They're still negotiated so that the wheels don't go into the surface or the wagon doesn't leave the surface. They negotiate, and the surfaces are happy. But the force that the ramp is now exerting on the wagon isn't straight up anymore because the surface isn't horizontal. The force the support force of the ramp is perpendicular to the ramp surface. It's that way. It's up and at an angle. Is that okay with everybody? It can't cancel a force that's straight down, i.e. the wagon's weight. They have a problem. Weight straight down, support force is up at an angle, they can't cancel. The best they can do is come close, and with the added issue of trying not to allow the wagon wheels to go into or off of the surface, those two forces, support force up-ish, and weight straight down, they sum to a leftover, what I call the ramp force, that points right down the ramp, perfectly down the ramp, and it causes the wagon to accelerate if you just let it go. So the wagon it's sort of falling. It's a reduced fall. It's a lovely constant acceleration downhill, and it depends on how steep the ramp is. If the ramp is barely a ramp, it's almost a cancellation. Not quite, but almost. And the downhill ramp force is very weak, and the wagon accelerates very slowly. If the ramp is super steep, the cancellation is terrible, and it accelerates like crazy. And the extreme case is this ramp, which isn't a ramp at all. It's the full acceleration due to gravity. Okay? So you know your whole life, the steeper the ramp is, the harder it is to deal with something on it, because the closer it is to going up a ladder. I mean, this ramp is useless, but a ramp like this is pretty tough to deal with too, because the forces involved downhill are huge. They're almost the weight of the wagon. All right. That said, okay, so I'll ask one of these questions. Here we go. And there it is. So if I push uphill on the wagon just hard enough to balance that downhill ramp force, so I'll bring in one additional force, force number 3, me. I'll pull uphill. And I'll pull uphill just enough so the ramp force goes, we cancel that out. What will the wagon do? You okay with the question? I'll get this out of here. There we go. All right. All right, we'll go to the 30-second mark here, and maybe a little more. 5-ish, 4-ish, 3-ish, 2, 1, 0. Ooh, 50-50. Okay, so there are 3 forces acting on this. 2 of them, the weight of the wagon and the support force of the ramp, sum to become the ramp force. So now we're down to, we sort of blurred the 2 together into the ramp force. And now I'm pulling up perfectly to cancel the ramp force. So the net force on the wagon is 0. Try this one again. Talk about it among yourselves. Get this. see whether you can shift that from 50-50 to all right. The net force on the wagon in this story is 0. All right, I'll give you 5 more seconds. 2, 1, 0. Yay. Still not 100%, but better. It is, the wagon will have net force 0, which does not mean that it's motionless. Leave the wagon, leave the ramp aside for a second. If I'm experiencing net force 0, I can be stationary like this. That's perfectly possible. Right now I'm experiencing no net force. I'm inertial. I'm the world's most, it's the most boring inertial there is. I'm not moving. 0, 0, 0. But I can also be moving. So not yet, I gotta get started. Okay, now I'm moving. I'm coasting along, inertial. I'm net force 0 still, but I'm not motionless. End of story. So things can coast even though they're not experiencing any overall force. And we did that day 1. It's the same here. This wagon, the wagon right now is experiencing 0 net force. But it can also experience 0 net force when I gotta get started, so don't watch yet. Okay, now. That's net force 0 again. It can coast. All right, so this is relevant to life on moving things like an escalator. Just because you're moving doesn't mean that you're experiencing a net force other than 0. All right? So, the correct answer, just to make sure is B. Right? That wagon, when you're canceling the ram force on it, so that it is a coasting object, it can be moving. And this is life most of the time on a ramp. You're pushing a shopping cart up a ramp. You're riding a wheelchair up a ramp. You're going steady, straight, constant velocity. Net force on you 0. Does the next question bring this? I forgot this question. Rolling wagon, it's still uphill as though it were on a ramp. Yeah, this is going right after, I wrote it a couple days ago, so I forget it. This is going after the problem set question. If I move this wagon at a straight and steady pace, it's going straight, as though we're riding a ramp. Okay, during that time, what force was I exerting on the wagon? You okay, the question? So, not yet, now. It's going in a straight line at a steady pace, as in constant velocity. I ran out of room. What force was I exerting on during that time? And you might think, well, how would you possibly know? You can know exactly. Are you okay with the question? Give it a try. And this one, go ahead and talk among yourselves about this. See if you can get this one right. I'll give you a full minute on it. All right. 10 more seconds. Three, 2, 1, 0. Dun, dun. All over the place. It'd be a bloodbath on the problem set here. Okay, how am I going to make progress with this one? Okay, I'm going to go exactly horizontal. Now I'm going. I'm at constant velocity. What's the net force on the wagon? 0. In which direction is the wagon's weight? Straight down. Okay, I ran out of room, of course. And I can continue it this way, okay? I'll go slower. The only other force on this wagon, other than that straight down force, is my force on the wagon. Which way is my force on the wagon? Up. And how strong is it? Equal to the wagon's weight, right? So that was horizontal. Did it really matter that I was doing it horizontally? If I go up a little bit, so it's still constant velocity, what's the net force on it? Still 0. It's coasting. Because it's going in constant velocity. It may defy your intuition, but if it was moving straight and true, steady, it wasn't accelerating the whole time, so the net force on it had to be 0. And if the net force on it was 0, and its weight was downward still, what was the force of my hand on it? Had to be straight up, because if it wasn't, it wouldn't cancel the weight. And it had to be equal in amount to the weight, otherwise it wouldn't cancel the weight. So the fact that I was going up at a cockeyed angle doesn't matter. Anytime you're on any vehicle or ride, a cable car, a bus going up a hill or down a hill, as long as it's going straight and steady, which means you're at constant velocity, the only thing the vehicle is doing is supporting your weight. You're coasting. You're being pushed. The vehicle is pushing you straight up to cancel your weight, otherwise you're going constant velocity. It's free. And I realize that's non-intuitive and it may sound irrelevant and all that stuff. But things that matter here mean that when you're on that bus, if you tilt the bus, it's a little messy because if you're on a bus and we grease the surface you're standing in the middle of the aisle on roller skates or something. And these are my old exam questions. You're on roller skates and you're moving at constant velocity in the bus and all that stuff. Will you drift towards the front or the back of the bus if you're on roller skates moving at constant velocity? Is there any force pushing you forward to keep you moving with the bus? No. Any force pushing you backward, trying to keep you, let the bus drive away from you? No, you're just, if you're, I didn't maybe make the question clear enough, but if you're on a horizontal bus and you have gotten moving at constant velocity, you got to this stage without hazard and disaster. You don't need anything to push you forward to keep you moving. You do it for free. You coast. That's inertia. And so as long as everything moves forward at constant velocity, you're fine standing there on roller skates, on a block of ice. It doesn't matter. You don't need anything to push you forward or backward. If the bus stops, you're in trouble. Because now you're going to be inertial. The bus will not push on you. It's your business. And the bus stops. You will keep going. And you will sail toward the front of the bus. You won't actually, you actually will be moving forward. The bus will be stopping underneath you, and nothing good will happen shortly. Is that okay? Questions about that? So this story requires you to think through it logically. It is right. This is very relevant to the problem set, those of you who have not looked at it. A bus, this is not quite the bus story because my hand can grip the bottom of this wagon despite the fact that we're going up cockeyed. You don't want to be on a bus on roller skates when the bus itself is physically tilted, because now it is a ramp and life is complicated. But this is not a ramp story. This is me holding the wagon with my hand, and whenever the wagon is moving at constant velocity, whatever direction you like, The net force on it is 0. And that means that whatever forces are acting on it must sum to 0. They must cancel. And the only two forces that matter are weight down, and my hand must be pushing straight up with a force equal to weight. So that's what you're doing when you're riding, for example, a cable car up into the mountains. You get on the cable car, you're dangling there, the thing's dangling with you standing on the floor, and despite the fact that you're heading towards the peak over there, the cable car is not pushing you toward the peak. It doesn't have to. All it has to do is support your weight and let you coast toward the peak. The fact that you're heading toward the peak dates back to when you first stepped on the cable car or when it first started up. During that period, it did push on you toward the peak. Like if I start my story like this and say, and don't say, well, wait a second. Let's watch the start this time. During the start, I do have to push it toward the peak. Right now I'm canceling it, the net force is 0 because I'm canceling the weight. To get going toward the peak, I'm going to briefly push it toward the peak. There we go, I did it. And now it's coasting from there on in. So all the action occurred right back there at the start. The same was true on the cable car. So when you first started up, then it pushed you toward the peak. Got you going that way. And then you coast for the rest of the story. Yeah, David? Does the cable car have to expend energy to support your weight? The cable car has to do work on you if you move in the direction of its force. So right now, the cable car, it hasn't started yet. No work. During the startup process, whoosh, it pushed you toward the peak, and you began to move toward the peak. It did work on you during that period. And it started to invest energy in you in two forms. One of them in the energy of motion, because now you're moving a little bit. And the other is it lifted you a little bit. So you got a little dose of energy in both forms. From there on, you are moving at this cockeyed angle, and it is pushing you straight up. So the force on you is up, and the distance you're traveling, the vector, is cockeyed here. But it includes some up. There's a little bit of up in it. You know, it's a lot of horizontal that doesn't count, but it's some up, and the up does count. So it's doing work on you. So in the act of carrying you like this, the cable car is investing energy in you. It's doing work on you, and that energy is going. Once you got started, the energy in your motion is constant. The added energy is going only into raising you higher and higher, giving you gravitational potential energy. Others? Yeah, Ron? Can work occur on you while you're coasting? Yes. If you're in an elevator, when you're in the middle of a ride on an elevator, on an 800-floor building, Burj Khalifa or something like that, up you're going, whoosh, you're in the middle, you're going at constant velocity straight up. The floor is perfectly supporting your weight, no more, no less. If you stood on a scale, it would read your normal weight, because it's telling you how hard it's pushing on you, which is your weight. So it's pushing you up, and you're moving up. It's doing work on you. So you're coasting, but it is doing work on you, investing it the whole way. Yeah, Wes? Okay, so what you're asking is it seems that the goal of this exercise is to make you accelerate uphill the whole way. So why isn't it pushing you harder than your weight? In fact, the goal is not to make you accelerate upward. This is movement at constant velocity. To make you accelerate upward, the movement would be different. It would be. That's not what it's like to ride a cable car. The cable car doesn't start off slowly and then go faster and faster the whole way. If it did, it would have to push you towards the end, that's true, and it would keep investing energy in you, and that would go in as kinetic energy, go faster and faster. This is movement at constant velocity, which is typical of a lot of stuff. The elevator, at the start of the ride in the elevator, it does speed you up. But most of the trip on a tall building is at constant velocity. It does not want you to accelerate upward. So it pushes on you just enough to support your weight, no more, no less.
So, but then, why is it that your weight wouldn't just cancel out the velocity? Why do you keep moving?
Why wouldn't your weight cancel out the velocity? Well, your weight and the floor, say, of an elevator, you are pushing as hard on the elevator as it's pushing on you. But those are on two different objects. This is Newton's third law problem, that the only force acting on you is the elevator's push-up. The other force that is acting on you is your weight. Those two can't sum to zero. But that doesn't mean you're motionless. It only means that you're coasting. Your movement depends on what you were doing a minute ago. It's your history. So velocity, you inherit velocity from a moment earlier. And you're going upward, you stay going upward. It works just fine. So this is the struggle to get, first off, to really believe that forces cause accelerations, changes in velocity. They don't cause the velocity itself. The velocity itself is inherited from what you were used to be doing. That's the inertia idea. Okay, so, but you got to sort of circle it a bunch of times and think about it, and then think about it again, and then gradually settle in. Watch all the things around life here. The people going by on their skateboards, the people bicycling by with no hands. We'll talk about how you can ride no hands, and it's a long story. Okay, it's all in our future. Lots of stuff coasting by, in which case the net force on them is zero, and in all likelihood, whatever's around them is simply supporting their weight, nothing else. They are moving because they got moving earlier. Yeah. Yeah. Okay, so the question is if I'm pushing the wagon up the hill, is my force on it, which actually, in like all likelihood, is a support force, as you said. Which direction is it? It is uphill. So if you observe this. This has gotten too much. All right. So if you look over here, and don't look yet, let me get going. Okay, now, well, what's my force on it, on the wagon? During that period, well, it was moving uphill at constant velocity. So that means the net force on it, this is the whole logical progression. The logic is, it was moving up at constant velocity. So I know for sure the net force is zero. I also know that wagons and ramps like this develop a downhill ramp force. And I've talked about where those come from. It's the imperfect cancellation between weight and support force. So I must be adding one additional force that perfectly cancels the downhill ramp force. I must be pushing it uphill just as hard as the ramp force. And that is exactly right. So when you push something up a ramp, this is finally sort of the what's the word for the grand result? This is the grand result. It's like when you push something up a hill in a wagon, which you commonly do at constant velocity. You maybe speed up and slow down a little, yeah, but for the most part, you're going at constant velocity. You are canceling the ramp force and letting it coast. There's a bit of starting process. During the starting process, you have to push extra hard uphill to get it going. At the ending process, you have to push a little extra gently to let it slow to a stop. But in between, constant velocity. You're simply canceling the ramp force. And you know from experience that the steeper the ramp gets, the tougher it is to push it up that hill because the ramp force gets larger. The cancellation gets worse between support force and weight. So you have to push harder. This is why, as the ramp gets shallower, it gets easier to push stuff up there. It's always proportional to the weight of the stuff. So if you buy twice as many groceries, you're going to be pushing twice as hard on your shopping cart. But to get the shopping cart to go up the hill, you just have to cancel the ramp force. That means you care about how steep the ramp is and how much groceries weigh. And to sort of finish the calculation, if you want to know how hard you're pushing, you can actually figure that out. And the way to do this is using energy and work, which may not seem like the obvious path, but it's a great path. And the idea is this. Let's suppose this ramp takes you, I'm not going to do it as a question, I'll do it as life. Suppose this ramp, in going along the surface, it lifts the shopping cart or wagon 1 meter for every 10 meters you go along the surface. 10 to 1. So it's 10 of tilted surface versus 1 up. That means that in going along that surface, you do the work necessary to lift the wagon 1 meter. You do it in 10 meters, 10 times as far. So instead of lifting it straight up, which would take you a certain amount of, you'd have to exert the full weight of the wagon to carry it up a ladder at constant velocity. To go up this 10-to-1 ramp, you only have to push with a force that's a tenth as strong as its weight. It's uphill, which is fine, and it's 1/10 as strong because you're doing the work in 10 times the distance. And if force times distance, if you reduce the force involved by a factor of 10, if you increase the distance by a factor of 10, you reduce the force by a factor of 10. That's where you get 10-to-1. So this is things like the ADA, the American Disabilities Act, it regulates the steepness of handicap ramps. With this in mind, that the average, I think is it 12.5-to-1? I forget what it's something in that order. Like the ramp has to be 12.5 meters long to rise 1 meter, or shallower than that. That's the steepest you're allowed to go, because beyond that, some good fraction of people won't be able to propel themselves up the ramp anymore. It requires too large an uphill force to cancel the downhill ramp force. Okay? Let me see if I've got any more pieces to ask you guys about. One more that I will ask you about. Ooh. What was? I forgot what was the question. Which one was up there? What force am I exerting? Is it this one? Ah, that's not help. Oh, come on. Is that it? The correct answer is A, an uphill force equal in amount to the wagon's weight. You're just supporting it so it can coast. That's all. Let me ask you this last one. How does it do that? That's not the one. I don't know. I've lost it. What I did want to, the question I wanted to ask is this one. If the wagon is on the ramp, and I have done something with it, and we look at it at any moment, what can you tell me about the ramp's velocity and acceleration? And I'll answer my own question, is that you can't be sure what the velocity of the wagon on the ramp with no hand involved. You can't be sure what the velocity is. That depends on what it was doing a moment ago. If I pushed it up there a moment ago, the velocity would be uphill. If I let it go downhill a moment ago, the velocity would be downhill. We can't tell. What we can tell, though, is if that wagon is on the ramp and no hand is involved, it is accelerating down the hill, for sure. It's experiencing a downhill ramp force, and it's accelerating in accordance with Newton's second law, which says the ramp force divided by the mass. That will tell you how it's accelerating. So things that are on ramps, you can't tell how they're moving at this moment. That's velocity. You can tell how they're accelerating. That's caused by forces. That's happening now. You can predict it. All right, I'll stop, and we'll continue on Wednesday.